Hello everyone, I'm Hadrien. So I'll be presenting the workshop today, and I'm working with Refran on the smart contract and the upgrades plugin. So let's jump right in. Today's topic is about NFTs and more particularly how to mint NFTs, which I think is an interesting topic that can leave for a room for a lot of creativity in the developer space. So first, a small word about OpenZeppelin. You might know us already, but we dedicate our mission to protect the open economy, which we do through both our products that are the smart contract, the upgrades plugin, and the Defender suite, but also through security audits. And we are trusted by a lot of actors in this ecosystem. So we are very proud of what we offer, and we are also proud of offering tools for all your steps in the development of your app. So starting by writing your contract, managing your on-chain infrastructure with Defender, and also doing the proper auditing work before going to mainnet and basically holding millions of dollars worth of assets. So wherever you are in your development phase, OpenZeppelin has tools for you. So be sure to check them out, and hopefully we will help you build a more secure application. Before we start, we are hiring. We have a lot of open positions. So if you think that your profile fits or the needs of a company like us, feel free to apply. We are a very welcoming team, as the other member will probably say. I joined just a few months ago, and I think it's an amazing workplace. So feel free to apply. So first, ERC712 NFTs. Before we go into the details, most of you should be familiar with what it is, but let's just have a very quick view of what they are used for. And in the end, people think about collectibles, about CryptoPunk, CryptoKitties, and that's part of what an NFT is. But at the blockchain level, an NFT is just a way to track the ownership of a digital asset. And this digital asset can be a collectible, but it could also be something more abstract, like an ENS domain name, or even a liquidity provider, a position on Uniswap V3. These are NFTs as well. So you should think about using NFTs, not only if you are dealing with collectibles, but whenever your application contains ownership information about anything out there. Maybe interfacing with an NFT standard is very useful. It could be useful, in particular because it will make your application compatible with wallets and services like OpenSeas for doing auction and all that kind of interesting things. At OpenZeppelin, obviously, we have a smart contract for a suite of smart contracts for building NFTs. And we have this wizard that is a decently new product that you should definitely try out. And it's available through our website and our documentation. And this wizard is here to help you build your smart contract using our modules, and by basically putting in the features that you need and only the one that you need. So here we are an example of the wizard being used to deploy and to create an ERC721, but it's also available obviously for ERC20s and ERC1155, and it should help you better understand how to compose contracts using our modules. And we have a bunch of modules for ERC721s. We have a module called Burnable that allows someone to burn a token he owns or a token he is approved of. Obviously, you are not allowed to burn tokens from other users, but sometimes having the ability to hold to burn a token could be useful. We have enumerability features that can be interesting if you want to index data and you don't want to rely on an off-chain service like the graph, so you can have this data available on-chain. It requires storage, so it's a bit more gas expensive, but you are fully decentralized if you do that. There is a posable feature that some of you might want to use if you want your application to be able to be paused in case of like hazard recovery. This can be interesting. And also we have a URI specific module so that you have better granularity over the URI for each token, which is a useful feature when you want to interface with things like OpenSeas. So here we have a lot of features, but you might see that we don't have the minting part. And the minting part is somewhere that there is no generic way to do it. There are a lot of ways to do it. So if you go to the wizard and say that you want your token to be mintable, then we will add a safe mint function. And in this case, the contract is ownable. So only the owner is allowed to mint a token. And if you switch from ownable to roles, then we will create a minter role, and the safe function will be attached to this minter role, which is somehow similar. But in both cases, it's just a few persons are allowed to mint token. And in most cases, you don't want anybody to be able to mint any token. Otherwise, your application loses its purpose. For example, in the case of POAP, if anybody was able to mint any POAP token, they could say that they were at an event where they were not, and it would destroy the purpose of POAP. So controlling who can mint token is very important. Sometimes it's part of the process, like in CryptoKitties, you can have two CryptoKitty breed and create another CryptoKitty of a higher generation, but that's specific to this application, and in some cases you want to do things differently. So the question is, what is lazy minting? What are we going to discuss today? And what is it? Why is it useful? Well, the thing is, minting a token today is very expensive. I mean, the gas prices have gone down over the past weeks, but they are still decently high. I mean, I used to think that 80 gigawatt was a lot. And obviously the ETH value is also at the all-time high today. So when you multiply the two, minting a single token is almost $20. And this is, I believe, very expensive. And see it from an artist point of view, if you were to mint 100 tokens would be $2,000 already. So this is a lot. And maybe you want a better option than just paying for minting token in the first place. Maybe you can delay that. Maybe you can have the user pay that. So what if the initial owner could mint the token? I mean, unless someone is actually going to have the token and use it or consider it as a value, you don't really need to mint it in the first place. So this is a very interesting thought experiment, but unless someone needs it, it doesn't have to be on-chain. You only need it on-chain when someone has to prove that they're actually the owner of the token. And this is where lazy minting comes in. And so the idea is pretty simple. It's let's have a minting account, so an administrator account that we have previously, that can authorize someone to mint a token, and then the user will just mint the token, and the user will basically create the operation that will transfer the token from address 0 to its address. And the challenge is to do that without the minter account having to send a transaction in the first place. Because if the minter account has to send a transaction, then it defeats the purpose of the token being just created by the user when the user needs it. So there are different ways to do that we will explore today. There are mechanisms that use signatures. So we'll see personal signatures, signed type data, and signature validation from contract. And every time we'll see something, you should know that OpenZeppelin has tooling. So we will see it through the scope of OpenZeppelin tooling that will hopefully help you doing that. And we will also see how Merkle-proof can be used. And I think this is a very interesting use case for Merkle-proof. So we'll see how to generate Merkle-trees, generate Merkle-proof, and use them in the context of NFT minting, but it could be also applied to other contexts. So first thing is lazy minting with signatures. So cryptographic signatures, you might be familiar with it, but again, it's a process that is at the core of what we call asymmetric cryptography. And it's asymmetric because you've got public and private keys. And a signature is just taking a piece of data with your private key. So your private key will be your wallet, and creating a signature out of that. And only the owner of the private key can do the signature, but the recovery can be done by anyone. And the idea is that if you have the same piece of data that was used to generate the signature, and you also have a signature, then from these two values, you can create the public key. And this can be done by anyone, and the public key can be verified easily. And in the context of Ethereum, the public key will be hashed, which will provide you with an address, an Ethereum address. So the idea is anyone with a private key can sign data, and we can do the recovery, including doing it off-chain and on-chain, to verify that the signature was produced by an authorized account, which is at the core of what we're going to do today. And so ECDSA signature, which are signature over an elliptic curve, this is technical things that are used by Ethereum, are used for two main things. First one is signing transaction. Whenever you sign a transaction, and then when it's verified, when it's included in a block, this is done using the private key of the sender. But the same method is also applied for messages, more abstract messages that can be used for anything, including, obviously, being part of a workflow where you mint NFTs. So I show on the screen here how you can do a signature for either a transaction or a message using ethers or Web3. These are very simple operations that are at the core of the blockchain. And the good thing is that the recovery, well, basically while building a signature requires the wallet, the recovery can be done by anyone, including someone that doesn't have the wallet, obviously, and it can be done off-chain using either ethers, Web3, or other tooling, but it can also be done on-chain. And this is where OpenZeppelin's tooling come in handy. We have this ECDSA library that contains an ECDSA recover, which is very helpful because you can just provide a digest of your message and a signature, and this will recover the signer. And so you can just take this signer and use it for any number of things. One thing is that I was talking about a digest. What you verify when you do a recover is not verify the raw data. The data is processed, is hashed in some way. And this is done so that there is no possible confusion between a signed transaction and a signed message. Basically, we don't want the message to be able to take any form, because you can trick someone into signing something that they think is a message, but that is actually a transaction. So the message, they are prepared by basically prefixing them with a small string and hashing them. And again, this is something that is done by the wallet during the signature phase, but that you need to do when you do the recovery. And so again, if you are doing it in Solidity using OpenZeppelin tooling, well, you just have to replace the digest with the ETH signed message hash of your message. And this is done again using OpenZeppelin tooling. So we have tooling for all of this. So let's go have a small demo here of what this could look like. And all the code that you're going to show is available on GitHub. So you have a link here. I'm sure the link will be sent to you again in the chat. And if you want to experiment with this tooling, I strongly encourage you to have a look at the code, both for the Solidity part and the test part, so that you are able to see it working by yourself, and maybe to use it as an example when building your application. So here on the left part, we have a smart contract, which is ERC712 lazy mint. This is a smart contract. On the right part, what we will see later, we have the test. But for now, let's just focus on the Solidity part. So this is a simple smart contract. We have a constructor. We are inheriting from access control. So this is to have a minter role, and the minter role is the one that is going to be authorized to produce signatures, but anybody will be authorized to redeem a token if they have a right signature. And this is done through this redeem function. Maybe I will increase the size a bit more. And this redeem function just takes the account and the token ID where the token should be minted to, and a signature. And you can see that this just does a safe mint of the token to the account. So this is just minting it. So all the security is in this require. And this requires, what it does is it hashes the account and the token ID. So there is a hash method. And once this is hashed, then the value is verified against the signature. So we'll have a look at what the hashing does. The hashing is just preparing the token ID and the account using the KSAC function, and putting that into the toETH signed message hash. So the function we saw before that is prefixing the hash. And then the verification is as simple as taking this digest that was produced by the hash function, putting it inside the ECDSA recover with the signature, and just verifying that the address that is recovered has a minter role. So here, anybody can redeem, and then you just verify that whoever did the signature has a minter role. So if you were to try to forward a signature, this test will fail. So in the testing part, we'll see it running to EtherScript just after. But just what you have to see here is that when you test this, basically you have to create a signature which is as easy as signing with account 1, which is the one that has the minter role. And when the signature is produced, you can just call the redeem function with another account, so account 2 here, which has no privileged access, and this will mint the token. So yeah, let's just try that. So this is the first test we have, and obviously the minting happened pretty well, and we see that that minting the token redeeming is a bit more expensive. It's about $21, so it's a bit more expensive than simply minting using an owner, because there is this whole signature mechanism involved. But what's interesting is that this price is not paid by the artist, but it's paid by the owner, and it only has to be paid whenever they want to actually own the token, either because they want to transfer it or because they want to prove ownership of that. And so just to show you how this can look like, let's just go to our folder here, and here I'm just going to start a hard hat node. So this is just a blockchain that is running right now. It might be small for you. I will try to increase the size. Yeah, and this is just a blockchain. It's starting to run. And on this side, what we're going to do is we have a script here that is just a script that deploys the registry. So yeah, I need to do that on network localhost. And so, okay, what is going on? This is a demo effect, I guess. Yeah, okay, yeah, I forgot to put hard hat run. So what we did here is we deployed an ERC20 lazy mint with ERC712 that we'll see just after. We created a registry here, and we got the address of the registry. And so now, if we just say that, hey, the address is this one, and also, by the way, the token ID I want is, let's say, 17, then I can just run my second script, which is a script that does a signature. And what you will see here is that this script is not actually calling the blockchain. There is almost no calls here. But what we see is that in this registry, we're trying to create token ID 17 to this account, which is something are hard-coded. And this is the signature we get. And so a cryptographic signature, this is what it looks like. And so let's just take this cryptographic signature and put it in an envar so that my script is able to get it later on. And so if I try to do the redeem call, then what we see here is, okay, we should have, okay, yeah, again, we need that. Yeah, we see that the redeem happened here. And so here we've got the result of the redeeming. And so this user here was able to redeem the token. And what you see is that the transaction that redeems the token here, this address, is not the address that deployed the contract here. So this address is not the address of the minter. Again, the address of the minter is something different, but thanks to the signature, it was possible to do that. And something interesting is if I try to mint a second time, what we'll see is that the token is already minted. So obviously I cannot do that. But also, if I'm trying to mint another token, like token 42, and I try to use the same signature, which obviously is not valid for token 42, I will get a revert with invalid signatures. So this is just showing you that this can very easily be done through script, obviously, and it can be done off-chain. And again, this is what a signature looks like. So it's not something completely abstract, it's just an hexadecimal string that is a proof of that was signed by the minter. Okay, so let's go back to signature and have something a bit more interesting, I think. This is the use of ERC712, because the signature we showed previously were done using personal sign. And while this works decently well, it has some major drawbacks. One of the drawbacks is that by default, personal signatures are not targeting any specific chain ID, any specific contract. So if you sign something, your signature is like universal for what you signed, and there is no way to know if you signed it for a particular purpose. And so some application may reuse your signature that you produce in one context, but in another context, and it will be difficult for the application to differentiate that. Another issue with personal sign is that you have very little information given to the wallet. So the wallet just asks you to sign the data, but the data can be abstract and difficult to parse. So the wallet doesn't know what to show you, and so it's difficult for you to know what you're actually signing. And so this is what ERC712 is trying to solve. Like the ERC712 is not ERC721. It's easy to get mixed between the two. Be careful when you're speaking about these two ERCs. But you can use ERC712 in the context of ERC721. And basically what ERC712 proposes is a domain separator that describes the context and a structure hash that defines also the structure of the data that the user will be signing. And so the signature verification process is a bit more complex. You can read about it in the ERC. But OpenZeppelin thankfully has tooling for that. And we have this EIP712.sol abstract contract. So it's not a library, it's a contract that you should inherit from, but it manages a lot of things like creating the domain separator, and it allows you to easily verify signature using the hash type data before internal function. Sorry. And this function is pretty useful. It's going to replace the prefixing function that we saw before for personal signature, but it's going to do a much more complex prefixing scheme, which will include the domain separator. And what you have to pass it is a signed or a hash of the structure, which contains both a definition of the structure. So here we are give it a structure which has a sender and a receiver, and then you put in the sender and the receiver. And what's interesting with EIP712, as I told you, is that unlike personal sign, when you sign that with MetaMask, you actually have an idea of what you are signing. If you were to sign complex data with MetaMask, this is what MetaMask would show you. And here the message is a bit abstract, and part of it is not ASCII, so you are having a hard time understanding what you're actually signing. And this can be intimidating, and it can be dangerous, not knowing what you're signing. On the other hand, with EIP712, the wallet is getting a full description of the message that you are signing and can show it to you. And so here we have a much better understanding of what we are signing. So in the case of this screenshot, this is a GSN meta transaction, but the same could apply to any other structures. And we have a better understanding of what you're actually signing. So I think it's a big improvement. So again, let's have a look at what this can be in the code. So let's go back to our example here of our ERC721 lazy mint, but this time we are using EIP712. And what you see that unlike the previous version, we also have to inherit from this EIP712 contract, and we have to define it. And here we are using a name, which is the name of the protocol, and we are putting the same name as a token because it's handy, but you could use any other token. And there is a version mechanism again also. So here we just call that version 1. And what you can see also is that the redeem function is identical to the previous version. And the verify function is also identical to the previous version. So it's the only changes is in the hashing. And basically what we do in the hashing is instead of doing an ETH signed message prefix, we are using this hash type data before, which is an internal function that is provided by EIP712. And we're just saying that, hey, we're just signing a structure that is an NFT with a token ID and an account. And so the signature will have to match both the domain definition of this token, so this contract. So it will be the contract address and the chain ID. But it will also have to match the specific of this token. And when you are having a look at the test, again, it's pretty similar. You see the redeem part is the same. What's different is a signature. in the first example, again, the signature was done using sign message, but here the signature is provided by the sign tab data primitive, which is a part of the Ether signer we have here, and we're giving it a domain which defines the target, and we're also giving it a definition of the type. So the type here is NFT, just like described here, and we're giving it the actual values. So creating this signature can look a bit more complex from a JavaScript standpoint, but it's much more secure because you know which token you are targeting, which chain you are targeting, and the signer, if they are using MetaMask or another wallet, will have a lot of information that will be pretty useful for them. And so if we have a look at this running, what we'll see here is that the cost is roughly the same. It's not that much more expensive than doing a personal sign. There might be a few hundred gas more because computing the prefix is a bit more complex, but it's almost the same. So I would encourage you to use ERC712 whenever possible, just because it's better for the signing process by the artist. Remember that the signers they are not the users, they are not the deployers, they are the one actually authorizing someone to create an NFT. So they are the artists basically. So you want to help them having a smoother process when signing authorization. Another thing that we can discuss is that this process here works well when what you are recovering here is a minter. But what if you wanted the minter to be a smart wallet? There are a lot of smart wallets out there. I'm thinking Argent, Gnosis, Ethereum was one of them. I don't know if they are still around, but there are a movement towards smart wallet, and this is just recovering recurring address that were used to sign. And sometimes you are not able to sign because with your identity because you have a smart wallet, but rather you are signing with a key that is controlling the identity. So in this case, you may want to have a look at our signature checker function. And this is an example of the EIP of the lazy minting with EIP712, but with the signature checker. And this is almost identical. The only difference here is that you have an address assigner. And when you are doing the verification, you compute the hash the same way, but rather than doing a receive recover, what you're going to do is to verify that the signer has the right role, obviously, and also verify that the signature matches the signer. So this is a two-step process. And this function here, which is something that is pretty new to OpenZeppelin that we just provided in the latest version, will be able to detect if the signer is either an externally owned account, and then the signature is recovered like we saw previously, or if this is a smart wallet. And so the example here would be in this test file where we are deploying a smart wallet, which is owned by the account one, but it is not the account one, it's just a smart wallet owned by it. And when we are doing the signature, we do it the same way using account one as a signer. But then when we redeem, we are saying that the signer is actually the smart wallet. And the library will detect that this is a smart wallet, and so it will use ERC1271 to verify that the signature was done by the owner. So this is more of an advanced use case, but if you are serious about supporting signature in an application, I strongly encourage you to learn about it. Okay, so let's go back to our slides, and maybe let's go onto the actual topic of the talk, which is Merkle drops. And the question is, when are Merkle drops useful? And the answer is when you are doing large airdrop. An example is you might have been a receiver of Unitoken after the Uniswap airdrop, and the Uniswap airdrop involved Merkle-trees, because basically they knew in advance who the receiver were, how many tokens they have, and so they were able to send that to encode that into the blockchain, and so users can just claim their part of the airdrop, and that's very interesting. One of the interesting part is that when you are doing an airdrop using a Merkle-tree like that, basically what you are doing is you are encoding the set of receiver in advance. So users know for sure that no other tokens will be minted later on, or they have a good vision of who the receivers are. So this, from an NFT point of view, can be very useful if you want to make sure that, hey, this is my collection of NFTs. There are 100 receivers that have been decided in advance. I will be able to provide proof so that each and every one of them can mint their token themselves, but they also know that no other token will be minted after the fact. So you have better understanding of the scarcity of the NFT. And so what are Merkle-trees and how they are used to perform Merkle drop is the core of this system. So if you don't know what a Merkle-tree is, and I'm assuming some of you at least won't know that, you can just go to Wikipedia and you will get a lot of information. But I think the core is in these two sentences. The idea is that it's just a tree, a binary tree, or it could be a non-binary, but in most cases it's a binary tree. And the important characteristic is that every leaf is labeled with a cryptographic hash of some data block. And every non-leaf node, so every internal node of the tree, is also labeled with a cryptographic hash, but that is constructed by hashing the label of the child. So basically, this is what a Merkle-tree would look like. You would have a set of data. Here is A, B, C, D, and E. And then you would hash this to produce your leaf. And by recursively hashing the parents of each node, you can produce the label for each node. And in the end, what you can say is that the root has a label that is a hash, a recursive hash of all the data. So if any piece of data that is used to build the Merkle-tree, then the root value would change. So just storing the root is very effective, because by storing just a single piece of data, you are able to store basically an identifier, a testimony of the entire data structure. So it's very storage efficient, and as you may know, storage is very expensive in a blockchain. So just storing a Merkle root is basically the best option. And so when you want to verify a Merkle root, it's pretty simple. You just need to have the data of the leaf and the hash of the neighboring node. And the hash of the neighboring node is what we call the actual Merkle proof. It's the path. And when you want to verify that, you just hash the data for the leaf, so you get the node for the leaf. And you iteratively hash the current node with the neighboring nodes that are in your proof. And you will do that and so that you go all the way to the root. And in the end, you are to be able to verify that the root you reconstructed matches the root that you have in your storage. And if it doesn't, then either your leaf or your proof are invalid. But if those are matching, and if your cryptographic function is secure, obviously, then you have a good proof that the data that is in the leaf is actually part of the root. And one of the key features in Merkle proof is that the length of the proof corresponds to the height of the tree. So it's logarithmic relative to the number of leaves, so relative to the amount of data you have in your tree. So you can have very, very large trees and still have very succinct proof that some data is in this large tree that is not stored on chain. Only the root node is stored on chain. And so this is how it would work. Basically, if you want to reconstruct this node, you would have to hash it with data from H4 to reproduce H7. Then you would have to hash it with data from H6 to reproduce H8. And then you would have to hash that with the value H5 to reconstruct the root and verify that. So there are only 3 values that you will need to provide as part of the proof. So this is very efficient. And obviously, OpenZeppelin provides tooling for that through the Merkle proof Solidity library. And basically, this is a very simple library that contains just one function. In this function, you just provide it a proof, the root of a tree, and a leaf that is supposed to be proven by the proof. And this will tell you whether the proof is valid or invalid. And this is what we're providing. This is what was used by Uniswap during the airdrop. And this is what you should probably use if you ever want to do this kind of Merkle drop of NFTs or of ERC20s or of any other asset. And basically, when you want to create the Merkle-tree is pretty simple. There is a library for that. So this is some piece of code that I put in the slide for people after the fact to have access to. But what we'll do is we'll have a look at that, at the same piece of code directly into my developer environment, and that you will obviously be able to check out in GitHub. So this is our famous ERC712 token, but in this case, this is a Merkle-drop variant. And you see that here, we don't have access control, so we don't have a privileged miner, but what we have is a root value. So this is the root of our Merkle-tree. And what's going to happen is that someone that wants to mint a collection of tokens will define in advance which token are part of the collection, and we'll just create this contract by providing the Merkle root. And then it's completely trustless. There is no privileged access, and anybody that knows the Merkle-tree, which should be public, and just create a proof and reconstruct that. And here we have the same redeem function that is very similar. Unlike before, we don't have a signature, we have a proof that has a different type, but that's the only difference. And so we have this verify function that just calls the Merkle proof verify. So unlike previously where we were doing cryptographic signature verification, this is a Merkle proof verification. And the only thing we have to provide it is basically the root that is stored as part of the contract, the proof, and the leaf. And so we just have to reconstruct the leaf. And so in our Merkle-tree, each leaf of the tree is basically a token that is going to be minted. So each leaf of the tree is a pair that contains a token ID and an account. And so if you want to rebuild that, basically what you should see is that we have a token.json file. So this is basically the core of my Merkle. This is my Merkle drop, but yours could be much longer and way different. And we've got token IDs, which are just integers, and we've got the address of the owner. So these are random values, but those could be IPFS hash, they could be sequential numbers corresponding to pieces of art, they could be anything. And so basically what we do here is that we build the Merkle-tree here using this Merkle-tree tooling, and we just provide it basically the leaf value. So the leaf value is just the hash of all the entries in our file. And we're saying that, hey, this is a KSAC 256 base tree, so this is how you should hash data. And you should sort the pair, and sorting the pair is a nice trick that allows the proof to be more succinct, because it allows you not to basically just know what the hash of the neighbor is, and not if it's a left or a right neighbor. So this is a trick that is very helpful if you want to have more succinct proof with no decrease in security. And whenever we want to mint a token, just like before, we have this redeem function, but unlike before, we're not using a signature, we're using a proof. And here, building a proof is just taking the Merkle-tree and asking it for a new proof that matches our token. So in this case, everything is local in my dev environment. But interesting thing that you can think of is that obviously the Merkle-tree should be public. So you might want to publish a file like the one I showed previously that allows anyone to rebuild the Merkle-tree. But you might even go further and maybe create a website that allows anyone to search the Merkle-tree and to interactively generate proof. This is not something we have right now. I'm not sure if there are generic generic tooling to do that, but it would be pretty easy to create a UI that does that. So if you are serious about creating Merkle drop, I think this would be a very interesting thing to see the transparency that a Merkle drop can offer by helping people create their Merkle proof themselves through a UI. And so if we are trying to use that to run that test file, what we see here is that the price is slightly by about 80 cents cheaper than using signatures, because basically verifying a Merkle proof is a bit easier than it involves less operation than checking a cryptographic signature. So this is one of the cheapest option, and also it is the cheapest option as part of deploying the smart contract. So this was not clearly visible, but if we run all our tests together, we will be able to have a resume of all the prices. And you see that apart for the smart wallet that I use for another test, the ERC721 that is the cheapest to deploy is actually the one that includes the Merkle drop, because you don't have to store anything regarding access control, authorization, minters, and everything. So this is the cheapest to deploy, and it's also one of the cheapest to mint. So yeah, maybe this basic one is the cheapest to mint, but can only be minted by the owner. And then they are a bit more expensive, and the only one that is barely at $20 is the Merkle drop. But this one has the advantages that it's not the artist that is paying this, it's the initial receiver of the token. So if you were to create, again, let's take the example of 100 pieces of art, the artist doesn't have to pay 100 times $19 to mint them and then transfer them to user. It can just deploy the simpler smart contract with the Merkle root already stored in it, and then user will be able to individually pay $20 each to get each pieces of art. So I think this is a much better option for users. So in conclusion, because it's already a bit long, we've seen a few options, a few cryptographic tooling that is available to OpenZeppelin contracts and that is available also in tests, so you can check this out. Those are ECDSA personal signature, sign type data. We very briefly speak about ERC1271, but I encourage you to read more about it. And we saw in depth how to do Merkle proof and Merkle proof verification. And what you should know is that those are not exclusive. For example, we saw that 1271 signature verification works well with EIP712 sign type data, but you can even go further and imagine a context where each Merkle root is not stored in the smart contract, but is provided with a signature. So someone would show which token they want to mint, prove that this is part of a Merkle root, of a Merkle-tree, and then have a signature of the corresponding Merkle root by the artist. That way the artist could basically just sign another Merkle root, and then an entire Merkle tree of token would be available to be redeemed by user. So try to combine those in a very creative way, and I'm sure you will be able to provide very interesting use cases and workflows for user and for assets. So this is the links that you should all know about. Obviously, OpenZeppelin contracts that we discussed at length during this workshop, but also feel free to go have a look at the docs where everything is explained. Go discuss that into the forum. And if you're serious about building a dApp, well, check out Defender, because Defender is probably the next place you want to go after OpenZeppelin contract, when you will have to manage your dApp on chain, maybe manage upgrades, manage security, get notification about activity. Defender is a great tool for that. So thank you very much.